Hello, this is Federico, and I have prepared this short video to show you what the model looks like in practice after being implemented and tested. I have divided this presentation into three parts. In the first one, I will explore what data I received from the Landmeetdienst and some issues I found with this data. In the second part, I will discuss what the difference with your current system and the new data model is. And in the final part, I will show you the case study. So I chose to test the model with a street reconstruction at campus. So I simulated this. So for the first part, the data received from campus and facility management was in fact received from the Landmeetdienst. And I have uncovered these issues while working with it. So some digitization problems. There is no information on how components are connected to each other. There is only one table shared between all of the components, few attributes, and finally this issue. So we will go more into detail about this in a live demonstration that starts now. Here I have opened QGIS and I have loaded the datasets that I received from the Landmeetdienst. It's one dataset with the lines, so this is cables, pipes, protective elements, and the appurtenances in the campus. As you can see, I have classified them according to the thema, data transport, gas low pressure, etc. And I want to discuss the issues I found with this data. First, if we zoom in here, you can see that the pipes are not connected properly to each other in many places. Here too, there is no connection here. Then, apart from that, the second problem is that there is no topological information, so there is no table that stores how this element is connected to this element, and if they are connected at all. And in the case that there was an appurtenance, for example here, how this element connects to this appurtenance, and etc. All of the connections here are not stored. The third issue is the attributes. There is one table which is shared by protective elements, pipes, cables, very different elements, and they all share one table where we store all of the information. This table is also shared by the points, so by the appurtenances, the street lights, the valves, the sleeves, and this is not the way that this sort of data is normally stored. It's preferable to use different tables for different components. Also, the fourth issue is the sparse number of attributes. There is only 31 attributes, and I would say this is not enough for doing operation and maintenance. And some of the attributes here, for example, are repeated. The bovengrond zichtbaarheid, so above ground visibility is here, and it's also here. And finally, there is this attribute text that is used to store very different sort of data, and ideally you would want each attribute to store a single type of information. And that's it. In general, the datasets are very complete in terms of what they were a few years ago in the AutoCAD file, so that is a plus. But the thing is, they need some improvement if they are going to be used in an asset management system. And that's it for this first live demo. The second part of this presentation is about what is this new model, what does it look like. It's implemented as a spatial relational database. So it's basically a collection of tables. Here I have made them schematically with boxes. Each of these boxes is a table, and the arrows show how they are related to each other. And for example, this is how you store a pipe in these tables. A pipe is a CT object and it has an ID. So some of the information goes in a table that is called CT object. But more specifically, a pipe is also a network feature. So we store even more information in a table called network feature. A pipe is of course a pipe, so the rest of the information goes in the table pipe. It has dimensions, as do all network features, so we store the dimensions of the pipe in this table, and so on and so forth. It has a material, it's stored like this, and it belongs to a network. So we follow this route, and we can see how we relate that this pipe ID 1500 belongs to the gas low pressure network. Essentially, the difference with your current system is that you had one table to represent all of this information, and now we have many tables. And this allows for much more complex analysis and to store more varied information. I will show you some of this in the next live demo. This live demo starts a bit more technical because I want to show you very quickly just how the connection to the database works. So I click here, and this is the program, the database program. It's called PostgreSQL. So I create a new connection. I give it a name, campus connection. It's in my computer, so local. The database, I have to be very careful and give it the name which I have given to it in the program. Then I simply put my username and password, and that's it. I have enabled this campus connection, and I will connect to it. And now, for example, I can add a view which is a large number of tables that I have joined together, so that you can see all of the information that this new model adds. So here it is. This is the gas low pressure and the district heating networks. They are the chosen utility networks for my work, and I will open a random element to see the attributes. And here you can see there is a lot of, this is not all of it, but this is a lot of new information added. For example, the function, the usage, the location accuracy, the dates, when it was installed, when it was begun its use, when it was registered, abandoned, etc. The slope, you can store the cathodic protection, the network it belongs to, materials, all in a standardized way. And that is, see all of this attribute information. This is the benefit of using the one. It's not so different from your existing system. It's just that the number of tables and the way of classifying the information is simply much more complete. And this is it for the second live demo. For the case study, I chose a street reconstruction process at the campus, which I discussed with Andrea as a good case to test the model. I divided this simulated project into 3 phases. In the first one, we identify what lies under the street that is going to be reconstructed. In the second one, we examine the maintenance history and the performance of the pipes to decide where they should be replaced or kept when the street is resurfaced. And in the third phase, the execution, we want to know and provide to the contractors that will be executing the work what the site conditions are, if there is water, if there is poor soil, and what are the depth of the components, so if they are buried at 2 meters, 1 meter, and what are the valves that shut off the flow to that location in order to ensure safety in case of an accident, for example. So we now go to the third live demo. In this third live demo, I will show you how I tested the model with a street reconstruction, a simulated street reconstruction at campus, and what are the consequences for the underlying utility networks. It will take a bit longer than the previous live demos because I will do a bunch of tests on the datasets. So the first thing you would want to do is to define where you're going to do the excavation, so the area where you will be working. I have saved 2 areas in my database, so I will just insert them now so that you can see them. I selected this place and this other spot here, just to give 2 examples. And the first thing that we said that is needed is to identify the components in the area. So for example, if I want to know what elements are in here, I simply open the database menu, and I have saved here what is called queries, which is simply the language used to retrieve information from databases. So here I want to select from my database the ID of the pipes, their name, the network they belong to, and I want to get that information only for the intersection of the networks and the excavation polygon, which I named one, which is this excavation polygon. So I'm simply going to and I'm going to load the result into the file so that you can see. Call it pipe scenario 1 and load it into the map. So if I turn off the view that I defined in the previous demo, you can see that these are all of the pipes that are located in this area belonging to the gas low pressure and the district heating network. So for example, this is an oil and gas chemical pipe, and here is information that allows to identify it uniquely. For example, the ID, the network it belongs to, the color, the material, the dimensions, its shape, etc. And of course we can do the same for this area. It's just a matter of changing the polygon, and that's basically it. I'm going to call it pipe scenario 2 and open it in the map. And here you can see that there are 3 pipes which are quite long, they extend beyond the area. And of course one would want to do the same for the appurtenances in the area, so valves, etc. So I have saved another query which now looks into the appurtenance in the area. I execute it and I save it as and there you can see all of the elements in the area. You can get the same type of information for valves. There is not much because there was not much information to begin with, only the class and its status. And in the next phase, let's see, the decision phase, we want to check out the maintenance history and the performance of components. So I have simply saved 2 queries that show this information. I'm going to execute the query that gets the maintenance history from components, and here you can see that a pipe may have several maintenance performed on it. This pipe with ID 1611 has corrective and preventive maintenance, inspections and rehabilitations, and you can see the reason why these tasks were executed. This one was simply an inspection that returned a leak. This was, of course, all of this information is fake. I have added it to the system just to show how it works. This was in June of 2010, and 5 days later I am saying, okay, it was rehabilitated and the leak was closed. And you can also show the information of who did this. The related party ID is 4, it's a contractor, and it's called like this, and the person who did the surveying is this company. And you can do the same for the performance of pipes. I'm going to execute the query to retrieve performance, and here you can see, for example, the same pipe 1611 has an engineer performance requirement of 4, and in the date where the leak was detected, it was given a performance score of 2, which is not sufficient. So this pipe had to be rehabilitated, or at least put in a queue for rehabilitation. And when it was finally checked again 5 years later, the leak was no longer detected and the performance was considered sufficient. This is just an example, of course. And at this stage, one might also want to know all of the related parties associated with each network. It's easy to retrieve. So, for example, we have 2 networks, district heating and the gas low pressure. And here you can see random names of people involved with this company, the organization name, and its role in the ownership or being a contractor or being an asset manager, and some contact information. This is just an example. It's much more complete what you can store in the model. The final phase is excavation, so the actual construction works on site. And the first thing you want to know is what are the site conditions. So I'm going to execute a query that gets the site conditions, and I'm going to load it. Sorry for the name, it's not the right one. But here, for example, I can retrieve all of the information related to having a safe excavation. For example, what are the groundwater levels? What is this groundwater level referred to? What is the soil type? What is the depth at which this element is located? What is the accuracy of these measurements, etc. And finally, another aspect of a safe excavation is knowing where the valves that close the flow to these components are located. So I'm going to run a query that gets the valves, all of the valves that close the flow to these gas elements in this area. And let's execute it. This one takes a while. And let's load it. To see it in the map. It takes a while to load. Here it is. This is the gas valve that closes the flow of gas to this branch of the network. There is none on this side because if you take a look at the rest of the network, it is broken here. So the gas only comes from this side and flows into this pipe through here. And this is the valve that closes the circuit. This is all for the explanation and for the last live demo. These are just a summary of the results for each phase. Here you can see how you show the components that are identified in an area. This is a summary of the maintenance properties of the components and of the performance. And finally, here we can see the valves to shut off gas and to shut off district heating, which is a closed circuit. There is access through this side and through this side, so you have to close 2 valves. And here is the information about a safe excavation: groundwater, depth, location quality, the color of the elements, etc. So this is it for the presentation, and if you could please give me feedback, positive, negative, what you think is missing in the model, it would be very much appreciated. Thank you for your attention, and I hope it wasn't too long.